And this is a little presentation on stormwater runoff for civil engineering. If I go into the folder, there's a presentation for stormwater and then a calculation related to stormwater, which is actually two. There's two calculations there. One of them is a sample one. Scroll down to the right spot here. We're supposed to do this for a little coffee shop, and because we all have the same data for that, you should be able to practice and everybody should get the same answers. So if you can get the same answers when you do that, then you know you did it right, and then you can move on to doing the calculation for your Habitat for Humanity house. Here's the deal with this one. Not hard. It's not hard. It's kind of like the heat transfer calculation, very tedious. You have to take your time. You have to focus on details. You have to pay attention to little things. It's very tedious. So here we go. A little bit about stormwater. Let's take a look at the presentation from Project Lead the Way. I am going to set up this slideshow so that we can see it on my screen. And there we go. So when it rains, the water has to go somewhere. And that's the premise of this particular presentation, is that where does it go? So at one point in time, there weren't buildings, there weren't roads, there weren't houses, there weren't cars driving on the roads, and when it rained, all of that water was absorbed into the ground and into the vegetation. However, now that we've paved roads, when the water hits that, it doesn't get absorbed anymore. It has to go somewhere, and then when the water's going somewhere, that's what we call runoff. When you put a building onto a site that used to be grass or it used to be a tree, the rainwater hits the asphalt shingles and it doesn't get absorbed anymore. It has to go somewhere. So we call that runoff. That's what runoff is. Typically, in the old days, runoff would just go into the sewer system, and the sewer system would go to the wastewater treatment facility, and they would treat it and then send it back to the people. But then, as more and more development was happening, the wastewater treatment facility plants can't handle both your sewage and rainwater runoff. So they had to be a new way of dealing with it, and to do that, a lot of municipalities now require to have what's called a detention pond or a rainwater retention pond whenever you're making any new site. And it's kind of a nice time to pause here for half a moment, because if I go on to like Google Maps and just show you some recent areas around us that have been developed, and when I say recent, I can go out this way. I'm just going straight down Appleton Avenue here. Where am I at? Here's Falls Village. Here's County Line. There's this cinema. I want to go just past County Line. There's that new Walmart that they put out there a few years ago, and here's the Menards that they put out there. Let's look at what this looks like in terms of satellite. If I zoom in on Menards here, there it is, right back there. That pond now exists because of Menards. They had to have a spot where their rainwater would go to, and when they put this facility in, this is the size pond that they determined they needed in order to house the water that would normally be absorbed. Here's the Walmart Supercenter over there. When this went in, used to be grass, so they had to find a way to contain the water that was there, and there's a pond right here. This pond is containing the water, so all the water that comes running off of this cement slab goes there, or right here, right out in front, that's a pond. And any new construction has to have those rainwater retention ponds near them. Any new construction. So if you zoom in and out on Google Maps enough now, you'll see them. Now, if you get into some of the older places of Menominee Falls, geez, here's North Middle School. It's been there forever. When they put North Middle School in, there's no rainwater retention pond around there. They didn't have those laws back then. So you have to have the rainwater retention pond in order to prevent runoff. I already talked about site development. Typically that's going to increase your runoff, and when that increases your runoff, you have to contain that water on your site somehow. I kind of already talked about this. They do things to contain the water, or maybe even when you're building, reduce the amount of water that's going to run off in the first place. There are things you can do when you build your facility that can change the runoff coefficients. So these are the things that affect your rainwater runoff. How hard is it going to rain? This number is going to be found on a table or a chart. What's the soil type? What is it hitting? It doesn't have to be soil. It could be the material, concrete, asphalt, shingle, any of those. What's the slope? The higher the slope, the more likely the water is to run off. What kind of vegetation is present? When we do our stormwater runoff, you're going to have to do two things. You're going to have to calculate what it is before you start developing the land, and then what the runoff is after you develop the land. And then you have to compare those two numbers. If you are increasing the amount of rainwater that runs off of the property, you have to do something to fix that. So you have to, that's what this slide is about, you have to do something to be able to make sure that you change and keep the runoff the same. You are not allowed to have any water run off of your property anymore. So you have to contain it on your property somehow. We will not use the rational method in class. So we're going to use an adapted version of this called the conservative method. But this is the formula basically that you need to calculate stormwater runoff. The runoff is equal to whatever the material is. So C represents the material, I is the intensity, and A is not area, but it's the acres. So it is the area, but it's done in acres, and it's how many acres of that area you have. So here are those variables defined. We're going to use what's called the conservative method. And the conservative method is going to include this coefficient, and it also does some things with this coefficient here as well. So ours is going to have two coefficients in it. Everything else is the same. This just has to do with the reoccurrence of the rainwater. How often is it going to come back? And it's going to tell you that in the problem. So maybe this is a good time to jump back to that problem that I was referencing before when we were showing things, if I can find it here. There we go. This problem up here tells you, this is the coffee shop problem, that we are going to plan for a 25-year 1-hour storm. So 25 years is the reoccurrence factor. They're going to say that this storm is going to be bad enough that it happens once every 25 years. Just so you know, the bigger the reoccurrence, like a 100-year storm is really bad. And a 10-year storm, not so bad. That's a storm that happens once every 10 years. So a 100-year storm is like the storm that's so bad that it only happens once every 100 years. So that coefficient factor, that's going to be on the next slide here. There it is. So for a 100-year storm, we're going to use the number 1.25. For a 25-year storm, it's going to be with the number 1.1. It's not going to change during the calculation. It'll stay the same all the way through. Intensity has to do with how much rainwater falls for how long. So when we say a 1-hour storm, that's going to be the rain that falls in 1 hour. This number is going to be found by looking on a chart, like this one right here. And the chart that you get when you're trying to do rainwater intensity will look exactly like this. I'm going to show you how to use that chart right now. And when I show you how to use that chart, I'm going to go to your assignment again. So I got to find that assignment. That's not it. I keep clicking on the same thing. There it is. And this link will take you to the place to find your rainwater intensity. So for example, if I'm trying to find this spot near Chicago, I'm going to click on the link. And then since I'm trying to get near Chicago, I might as well pinpoint right in on there right away. So here's a map of the Chicago area. Might as well drag this little crosshair, you can drag it around. I'm going to put it right on Chicago. Boom. And then I'm going to zoom in a little because I'm supposed to be near the University of Chicago. And if you don't know where that is, well, we'll find that right now. And it's actually, I'm pretty close. It's right down here in the main strip, like right in this area. Probably a little closer south, a little bit more south, but that's close enough. So a 25-year, here's 25-year, 1 hour storm. This says 2.46. So this is a 25-year, 1 hour storm. Oh, hold on. Up here, I have to change this to intensity. And when I change that to intensity, now I can read the map. 25-year, 1 hour. I actually didn't change. The number I used in my calculation when I did this for the Chicago problem was 2.42. So maybe I had this little cursor in a slightly different spot. And it does adjust when you put it into different places. So I use the number see there it goes, it adjusted to 2.45. When I did this, when I did my work, I used the number 2.42. So you might want to think about that when you're doing the problem. I'm telling you what it is right now. When you're doing this problem and you need the intensity, I used a 2.42 for that. And then once you have your intensity figured out, you can do the rest of the problem. You'll need to know your acres and the coefficients. So this is an example problem. The example problem is really good. They're telling you that they have a 3-acre farm near Nashville, Tennessee. And you're going to have a 30,000 square foot asphalt parking lot put into the place. So if you're going to do that, you're going to use the formula of rainwater runoff equals the coefficient factor times the C, you get this off of charts, times the intensity times the acres. And so they're going to show you a sample calculation. You have a 3-acre thing to begin with. You got to look up the intensity on that chart that I just said. And when they looked it up, it's for a 25-year, 1 hour storm, so they're going to use 2.54. And the runoff coefficient, since it's farmland, you get that off of a chart. Let me show you that chart for a second, because that chart is also something you're going to find in this assignment. It's right here. So for farmland, farmland goes from 0.05 all the way up to 0.3. So when you're doing your pre-numbers, you're going to average those. And when you're doing the pre-numbers, you're going to average them. So that's what they're doing right here. It says use the average. And they're going to use 0.18. So at this point, they have 1.1 for the CF, 1.8 for C, intensity was 2.54, and acres was 3, so they get 1.5 cubic feet per second. And then what you need to do is that's the before, so you would do the same formula for the after. Now they're going to put in a big, I'm going to go back a couple slides here. They're going to put in a parking lot. And the parking lot that they said they were going to put in the sample problem is going to be a 30,000 square foot parking lot. So not quite 1 acre. After when you're going through, not quite 1 acre. So at the end of this, you're going to have two different areas. You're going to have your parking lot, and you're still going to have the land that you didn't touch at all. So for the post-development, they're taking their parking lot and they're converting it to acres. So like I said, it's not quite an acre. This is the conversion factor. You take the square footage. 1 acre is 43,560 square feet. So you just do a little conversion and you convert that to acres, which means the remaining part of the land is going to be farmland. So The other thing that you got to know when you're doing your post-construction values, pre-construction you always average the numbers here, but now for post-construction for farmland, you're going to use 0.3. 0.3, you don't average them. We're using the conservative method, which means we want to overestimate the amount of runoff we're going to have. So we use 0.3, and then since we have a parking lot, I mean, whether it's asphalt or concrete or whatever, it's going to be 0.95. So we would not average these. We're going to use the highest value that you have when you're moving forward. So if I go from this current slide here, there's our parking lot and our farmland again. The intensity is not going to change because we're still doing this for the same storm. But you do use different values for your runoffs. The farmland, we're not using 0.18, we're using 0.3. And for the pavement, we're going to use 0.5. I'm stuck. Oh, there we go. So in the post-development, what you do is you have to do the CFCIA for both the farmland and the parking. CF isn't going to change from the beginning of the problem. The intensity isn't going to change. The only thing that's changing is this coefficient. This used to be 0.18, now it's 0.3 because we're using the conservative method. And the acreage changed because we took some of the farmland away and turned it into parking lot. These two numbers should still add up to your total. When you do the CIA, the CFCIA for the farmland, you get one value and you add that to the CFCIA for the second value, and then the total ends up being 3.7. So comparatively now, you can compare the two numbers. The post runoff was 3.7, the pre-runoff was 1.5. This is an increase of 2.2 cubic feet per second, and you have to contain that somehow on your site. You could make a rainwater retention pond. You could have rooftop gardens. You could have water barrels. You could have all kinds of different things to contain that, but you have to do something in order to contain it. So at this point, you guys are ready to try to do that assignment. I'm going to get out of this PowerPoint presentation and not save it. And then what you guys are going to do, because we've finished the presentation, try to do that coffee shop problem and see if you can get it right. Like I said, it's not hard, it's just tedious. When you open up the coffee shop problem, it starts off way up here like this. And this is just kind of a recap of everything that was in the PowerPoint presentation. You don't have much to do until you get all the way down to here. And when you get all the way down to here, here's the coffee shop problem. So you're going to have to go through and do your pre-construction. And in this case, the post-construction has three things going on. You have your coffee shop, the parking lot, and then the rest of it, they changed from forested area to sandy soil with a runoff slope of 7%. So you use this chart right here to get your coefficients. Use this link to take you to the intensity map. I said I used 2.42 when I did my sample. So give this a shot, see if you can get it right. We'll check the work when I get back and go from there.